Very good.
So for the recording, what is your name?
My name is Jean-Luc Pelissier.
And what do you do today?
And I'm the CEO of Universal Instruments.
Excellent.
Out of upstate New York.
And before Universal, what were you involved in?
I spent my life in test actually after school and started very early as I was doing my PhD in IBM actually, involved in test and design validation using and developing.
That's good. Go.
Hi, I'm Sridhar Vajapey. I'm today interviewing Jean-Luc Pelissier, who is the CEO, President and CEO of Universal Electronics. Welcome, Jean-Luc, on behalf of the Computer History Museum for today's recording.
Thank you, Sridhar. It's a pleasure to be here and to be interviewed by you. And I'm looking forward to spending the next few minutes with you and talking to you about my story and my experience.
Thank you very much. Truly appreciate it. So tell us about your background, about where you come from, what you have done.
Obviously, I'm not born in Texas. I'm born in the south of France. And very early, I had a passion for electronic, and that came going through and buying components for actually solving some problem at home with my father. And I was immediately passionate and went and followed an engineering degree and schooling in France for electronic and microelectronic. And I had the opportunity to pursue with a PhD inside of IBM. And I was working in a test division in Compec in the laboratory of IBM in France, sourcing all components and all technology for the need of IBM in Europe. And I had the opportunity at that time to work with some of the best technology. And my charter was really to develop an electron beam tester that would be done and put together from bits and pieces, a microscope and scanning electronic microscope, and some hardware that we were designing actually locally, and computing capability and image processing capability behind to actually build something that would, by comparing image between a good device and a bad device, would create a mapping of the failure and allow on big and advanced gate array to really follow the failure through the clocking system and the propagation of the fault inside of the device. So it was a great place and a great place to learn, and obviously it was a design work that involved software and hardware. But I had in mind to be in the birthplace of electronic and really go to Silicon Valley. So as I was moving into IBM and actually contemplating moving in the sales force of IBM, Schlumberger came and offered me the opportunity to work on the very exact same technology that I had developed in IBM, but for commercial purpose. And that's at that point that I joined Schlumberger first in Paris to cover from a marketing point and marketing function the European territories, and quickly they moved me to Saint-Étienne in France in a marketing position for a product line, and I finally ended up a year later in California to manage all the marketing of their component test division.
So after IBM, it seems like you were an engineer at IBM and then quickly moved over to marketing. Was it the French aristocracy style that put you in marketing?
No, I think it was the grooming methodology and the development methodology of Schlumberger. In addition, it was a technology that was really fundamentally emerging at that time. We were only a few individuals in the world having worked on that technology, and Schlumberger proposed me several positions actually covering that product, and gave me the opportunity to select the marketing position and becoming marketing manager for that product in Europe. And I had never done that, but remember I told you that I wanted to move into the sales force of IBM. So obviously that was an opportunity to move into a space which I absolutely didn't understand and didn't know. Since, yes, for sure, I was a pure engineer, a pure searcher.
This was the IDS machine that you were trying to sell, the IDS 2000?
At that point, I joined Schlumberger to be the marketing manager for the IDS 5000 at that time in Europe, yes.
And that had some neat technology with it.
It was incredible. I mean, there was there was a group of innovation. You know, the first innovation was while every SCM available in the world would move the sample under the column, the concept in the IDS 5000 and the innovative concept was to be able to power the device. The device would stay fixed inside the vacuum chamber, and we would move the column that was very compact and optimized for voltage contrast and measurement, and the column would be moving on a stage under the device. So that was one breakthrough in itself, and moving the column was obviously a challenge. Moving it with accuracy and repeatability to be able to do some imaging, to be able to drive the electron beam from a CAD system, and the association of the CAD system and the mapping of the CAD system with the XY coordinate, if you want, of the beam and the column was the second innovation in the system. The third innovation being the user interface itself, which was fundamentally removing absolutely all of the knobs that you traditionally was seeing on a SEM, a traditional SEM, by having something that was totally transparent. And the goal of the product was really to put in the hand of the designer, not a laboratory PhD expert, that powerful system that will really focus on design and design validation rather than focusing on how do you tune the microscope to be able to make measurement or make voltage contrast images from the device.
So you basically had three fundamentally new technologies going into this machine, quite complex.
Between others, yes, there were. I mean, the integration of the CAD together with the column, and the mapping of the column, the capability to move the column, and keeping the device stable to be able to exercise it. And
so as part of marketing, I assume you took a wider role beyond this machine to sell the test equipment as well that Schlumberger inherited from Fairchild?
So we actually were a small group of people that started together in the same time to market that product in Europe. And in Europe, we had, as a competitor, we had CMS and Lintec in the UK. We rapidly gained a predominant market share in Europe, and Schlumberger, who likes to move its personnel quite often in between function and location, asked me to move to Saint-Étienne and start to be responsible for a new generation test equipment that we were launching at that time, which was called the ITS 9000 MX. So that was a 40 megahertz version of the ITS 9000 family that was developed in Saint-Étienne. And the team asked me to move down to Saint-Étienne and take the marketing function for that product.
Was the ITS the first move away from Sentry? The Sentry line of products?
Yes. After the Sentry 2021, the Sentry 50, there was a Sentry 15, which was manufactured and engineered in Saint-Étienne. That Sentry 15 became a S15 when the name of the organization changed. And at that time, the product were named S with a number behind, depending on the frequency and its performance range. In parallel, we were in the process of developing the first family member of the ITS 9000. And there were two products. One was an ITS 9000 FX, which was a 100 megahertz, based and developed in the US, in San Jose, on Technology Drive. And the other was the ITS 9000 MX, which was developed in Saint-Étienne. The difference between the two was that the heart of the system, the sequencer per pin, which was another innovative technology, the first I would say, iteration of that technology. The heart of that sequencer per pin would be implemented in CMOS technology for the first time for the 40 megahertz version of the tester, while the 100 megahertz version of the tester would be actually developed in gallium arsenide. First bipolar for obviously all of the pin electronic and technology touching the component itself, but the heart of the machine was actually initially in bipolar technology, and as we moved the performance of the ITS family, moved in gallium arsenide.
So, can you talk a little bit? Sentry and Schlumberger was, when I started my work and started testing microprocessors, the TMS 7000 line of controllers, the TMS 32032 and 16 microprocessors, Sentry was it. Sentry filled our floor. Can you talk a little bit about what happened to that roadmap and how the transition, what forced the transition to the ITS line? Was this a major step function change? What happened?
Yes, it was a major step function. You have to realize that even so, maybe it could be called a veteran today. The Sentry 20 and 21 and the Sentry 50 were the beginning of my career, right? So from a timing perspective, everything that was prior to that, and as well as the beginning of the Sentry 20 and 21, I was still in my, I guess, in my crib. I've limited either recollection or just because, I've heard stories from the people around us. A great person to interview here to get all of that history would be Rudy Garcia, if you remember Rudy.
Yes.
Rudy, I think, is still having absolutely all of that history and would be a great interview for the museum, actually. So the Sentry 20 and the Sentry 21 were really the product that were selling at the time I joined Schlumberger from a test perspective, right? In parallel to that, and those were products that were coming from the US, so from Technology Drive, right? In parallel, we had that organization in Saint-Étienne in France that had recently introduced the Sentry 15, which became the S15, and its successor, which was a mixed signal tester on which dark ADC test capability were bolted onto a digital tester, so probably the first SoC tester, which was called the S1650. Okay, and at that point we were starting seeing in the industry some tester with resource per pin, right? And I'm certainly not recollecting exactly the chronology, but I think Megatest was certainly in that package, and probably LTX with the Trillium machine were there also, and therefore we had really a major innovation, which was to take the concept of the tester per pin to its quintessence, if you want. And the idea was, can we sequence more than one vector, if you want, on the pin electronic? And that's where we came up with the concept of the sequencer per pin, which would allow us to sequence a number of events on one and driving one pin electronic, if you want. And that really operated a complete break in the infrastructure of our tester, And that's when we embarked from the Century and Series 15 or 50 type of architecture onto the ITS 9000. And the ITS 9000 were, the ITS 1000 MX and FX at the beginning, and the evolution of the FX into the IX, KX, EX, and it's probably not the right order, that successfully went from 100 megahertz to 200 megahertz to 400 megahertz and to 800 megahertz.
The first ITX, the FX version and the MX versions, they were in early 90s?
They were launched, if I remember well, in, I would guess in 91.
91,
Yes.
That was a while back.
And so they were the first tester that included the sequencer per pin, which was a major innovation from a pattern generation, not a pattern generation, but from an event generation perspective, and allowed us to generate some very and extremely complex waveform at the pin electronic level, therefore getting more fidelity out of the test environment we are providing to the component. The second thing that we had to introduce is there was so much power dissipation and so much energy in those test equipment that we had to cool pretty much every single board with liquid. So we embarked in the same time that the design of the electronic into successive generation of technology dedicated to cooling effectively the electronic that we had in the tester. So for the first time, the tester would be organized in cages. There would be a control cages in which all of the pattern generation and the sequencing of the tester itself would be generated. And there would be cages in which we would provide the pattern generation for every pin and the generation of the event sequences for every pin. And then very high-speed cable, that was another challenging technology, would take the signal from those cages and pin slice, as we were calling them, and bring those signals to the pin electronic that were in a circular test set, obviously outside of the frame and the main frame itself.
So again, there were a whole bunch of innovations that were required to take it to the next generation. How do you, from a business perspective, balance the innovation piece versus risk? What drove, what all did Schlumberger, what all did you and your team consider when you were making decisions? Was it concurrent engineering? Was it you had to choose from a number of...
Well, obviously the ITS 9000 architecture was dramatically different from what was existing before. So that was a complete departure. The initial design and initial concept, even so I was still in France at that time and working on the diagnostic equipment, was generated from the innovation brain of an incredible engineering team that we had in both San Jose and Saint Etienne at that time, right? And there are many names that I could remember and highlight here, but a very innovative set of people. But very quickly, our kind of claim to fame on one side and our way of working with customer, we really got engaged very deeply with customer, I think very early on, developing technology on a roadmap that was defined by a number of customers, if you want, right? And now we would define the test equipment by the performance that that group of customer would require at a given point of time to meet the need of a technology node, right? And we would not necessarily balance the risk at that time from that perspective, but we would see what are the elements of technology that we need to really advance in order to be able to meet that technology node and to meet that particular performance requirements, right?
So it was pretty much concurrent engineering as you got the customer inputs, you knew their roadmaps, and you needed to rev your machines.
Yeah.
You looked at the technologies and concurrently started developing.
If you look at the ITS 9000 FX, really in the same time, you had a pin electronic capable of delivering signal at 100 megahertz, which,
At that time was very
high performance
right.
pin electronic, maybe 4 designers in the world can do or could do the design of that.
You
chip.
could almost name those designers.
You can definitely name those designers with no doubt, and know which one were better, and the one that were follower, and the one that were the most innovator. We would obviously all rush for the technology bed in which we would make them. So the foundry that would be willing to work for a relatively small volume of tester like we were, and to invest all of the development necessary to develop the simulation technology and to develop, and mature that bipolar technology to the level that where we needed it in order to meet the performance point of the tester. Then, in parallel to that, we had to develop the technology of the sequencer itself, and the technology of the sequencer has always been on the absolute cutting edge of the semiconductor technology available, right? So the first iteration were, as I told you, in bipolar, yielding those devices were an absolute challenge right from the beginning. Probably a little bit similar to what you have been experiencing in some, maybe in some example. And we moved from bipolar technology to gallium arsenide technology, which was obviously another element.
It was still in its infancy phase at that time.
It was
and the reliability factors were low.
And the reliability factor were low, which conducted us to make very early on in the choice of the technology platform, if you want, having the design, the requirement to move to liquid cooling, right? So I think, obviously I don't remember very well, but I think we were pretty much the first one to come up with liquid technology and liquid cooling technology for both our pin slice and our tested card, which was a pin electronic, and maturing that technology, which we can think is a little bit more, mechanical, yes, for sure, tube and plates, and but finding the right coolant on one side, right, that would not create problem in case of a leak or in case of an issue, and finding the right and designing the right valve that would allow us to pull that board, put it back, pull it again, put it back, was very, very challenging. And, in time and in terms of elapsed time, I'm not sure it didn't take us more time to really find the right technology for something that could appear to be relatively simple, like the valve, in comparison to the integration level and the complexity of the timing generator that was the sequencer per pin itself. So there are some really, good story and good anecdote about the concurrent design of obviously all of those technologies together.
So when you shifted over to the IX testers with gallium arsenide and liquid cooling, and possibly some other items as well, were there any that made you trip over? And if you did, how long did it take you to recover? Because recovering is part of a critical portion of business.
Well, I think like in many different places of the high technology, you come to a point where you are working a little bit in the unpredictable, right? Again, pin electronic and timing generator for all of that generation of tester being completely at the edge of the technology.
Right.
That means the technology node and the technology available was defining absolutely the performance of the tester, right? And our designer would take the simulation and take the fundamental capability of that particular technology, and from that put a stake in the ground in terms of saying the performance of the tester using that technology is going to be that much, right? And obviously it was always
Pushing the edge.
pushing the edge, right? As a result, on the design point of view, and depending on the quality of the design tool, the fidelity of the simulation and the simulation tool and the models that we're using at the transistor level and then at the subsystem level or the sub-block level would be extremely important in us meeting reality or just creating a problem. Then behind that, those were at that time technologies that were in the level of integration that we're looking at, extremely challenging in terms of defect density and therefore being able to yield those components. So I remember, generation of tester where, the tester would be ready with, I'm talking about the prototype here or the number 2, or the prototype, and literally, receiving wafer with timing generator from, our selected supplier that were working very, very hard to get us that technology, and maybe getting one good die, therefore one pin every one wafer or every 2 wafer, and struggling in terms of understanding if we would be able to really run that technology, and the number of weeks would come by, and we would get pressure obviously from customer that were reaching their own technology node, needing the tester in volume quantity, and the pressure and the rush and the management and the focus that we had to put from an engineering perspective to yield those components and be able to deliver the volume that was necessary to run the tester and the equipment in production were critical at that time. That was really critical. And when we stopped doing that in so bipolar first and then gallium arsenide, and we finally reached a point where we could really do high performance timing generator and sequencer using CMOS technology. And here again we would push the technology to the absolute extreme edge of its envelope, to the point where we would do a design and then a redesign, and what happened between a design and another redesign. It's 14 weeks, which is the cycle time of your fab. So there was adding a lot of pressure and a lot of I would say management and focus in the process of coming up with it.
As much as we used to laugh back then, 14 weeks cycle time, it is pretty much going to exceed 200-day cycle time as we move forward.
Yes.
So huge changes in semiconductor cycle time and so on. So in the case...
And the last technology change really has been, FPGA, right?
Yep.
And that's really when we saw that we could implement the technology and the complete tester inside a reconfigurable pin slice, if you want. And that's really when the concept of Sapphire came out, right? And here the challenge was not anymore in the timing generator. Even the timing generator, we were trying to pack so much pin inside of the timing generator to maximize the number of channels per board that we ended up with the same problem, or the same challenges, if you want, right? But we enabled another set of real issue and challenges by trying to push the FPGA technology to the level of being able to create the at-speed pattern generator that we are looking for, without maximizing the size of the pipeline and so on the tester. So a lot of other challenges.
The theme seems to be pushing the technology at every node.
The theme in that industry until design for testability and DFT technology came aboard has absolutely been pushing the technology to the absolute edge of what it could provide, either from an integration perspective or a combination of integration and performance perspective. And you had a compromise to do between the number of channels that you would pack onto one slice of a tester, versus its obviously absolute performance in speed and accuracy. Accuracy, we didn't talk about accuracy yet, but accuracy was, the element in which we could bring value to our customer at the very high end of the technology fringe, giving them the opportunity to themselves select out of their production of devices that were more or less fast, depending on where they were in the distribution of their process curve on their manufacturing.
So it's funny, isn't it? The testers reached $8 million per tester at some point in time, and DFT basically, once DFT techniques picked up, the need for such complexity dropped. And my guess is that the cost of the tester now dropped. That would have posed a big business challenge for you trying to keep the revenue growth. Can you talk about what the company went through when the price changes were so dramatic?
So, and that not, so, they were...
So this is still the Schlumberger time frame, I'm assuming.
It was absolutely
before it spun out.
It was just at the time of the spin-off, right? That transition happened, and so we were on the path of the ITS 9000 with its successful and subsequent iteration with more and more performance, better and better accuracy. When one of our customers asked us to do and to work with us to do a structural tester, right? So the idea was obviously that the device to be tested would embed a lot of functionality that would put the device into test configuration that the device itself would verify and really kind of deliver signature and result of those own internal tests to the tester in order to verify their validity and if the device had passed or had not passed the functionality that was required. And there are a lot of different type of DFT structure, and therefore there were a lot of different type of requirement for the complexity of the analysis to be done there behind by the tester or the pattern generation to be generated, right? At that stage, so we saw the beginning of a transition, from a tester that was, between, as you say, between $6 and $8 million at the high end, and a tester that would come down in terms of cost, and where the challenge would be really integration and the number of pin down in the sub $1 million, or hundreds of thousands of dollars if you want per unit. Now, the good thing is that transition didn't happen really, abruptly and overnight, right? Now, on another hand, we, in parallel to that, came up with the Sapphire platform and concept, where we were, jumping from that pattern generation being done in custom logic to the pattern generation being done by an FPGA, and being able to reprogram the FPGA almost on the fly, or at least during the execution of the various sequences of a test program, to be able to change the behavior of a pattern generator for its requirements, right? And that, together with the migration from the gallium arsenide technology to the CMOS technology, both on the pin electronic and on the sequencer per pin, if you want, and being able to pack that into slices of tester as a result of that, where the pattern generation would be really literally not done in a control mechanism and a control crate, but literally on each of the pin, and all of those pins would be synchronized together through a very ultra precise burst that could span the technology requirement from the gigahertz to the 50 megahertz or 20 megahertz in low-end application. At that point, really, the value proposition and the cost base that we have seen in the product was going to drive the cost of high-end tester down by a factor of 2 to 4, and 4 to 6 on the low-end tester, together with the layering of functionality that you could integrate a lot more, like the DFT technology. So we knew we were going to help the revenue base, right? And
so you needed the money somehow to continue to feed the massive engineering team.
We were, yes, because as you know, engineering a new generation tester is a very important entry barrier. And you are talking about it's in the hundreds of million range over the year to develop all of the functionality and the capability, right? So it was a challenge, and the bullet needed to be beaten, right?
This was also at the time Schlumberger had just spun off the test division.
It was at the time that the division had been spun off, and obviously we were restructuring the business to be standalone, right? And it was, as a result, the ideal time to make a structural change inside of NP Test as a reason of all of those changes. So
it was a perfect storm actually coming. It was a perfect tornado going right through the company.
I mean, there was so much change that changing the revenue base in the same time was going to be
hurtful,
but the right time to do it because it was transformation, if you want, right? And that's what happened. And as you know, somebody you know very well, Ashok Belani, really at that point, I think we talked about it so many times, and we really made the decision that we were going to be full-blown on that transition and really move on the other side, and that we need to do the thing that was right for our customers. And even if it meant that the revenue base would be reduced by a factor of 2 or...
This was around 2003, 2004?
Yeah, 2001 maybe, right? Because 2004, we really spun off in 2002, right? And we went public, I think, at the end of 2003.
For purposes of history, the Fairchild Division, the non-test division, got spun out from Schlumberger at around which year? In the 70s or 80s?
I think it was in the 70s, end of the 70s.
End of the 70s.
You would have to verify that because...
And
again,
around that, in that era.
But it was in that era. When I arrived in Schlumberger, that time was long.
Has happened.
Right. Yeah.
And Schlumberger had a good 15-year run with doing excellent equipment and selling them, at the least.
Well, again, I think there were those family of product, right? The Century 22, I will remember always, my...
You cut your teeth on them.
When I joined, so I was, this researcher, developer, engineer in IBM, right? And I joined Schlumberger, and I think 2 weeks or 3 weeks later, I am at Electronica, right? And here it's my first show, right? And I have this purchasing manager from well-known company in Germany that comes, and I actually with a purchase order of $45 million to buy 20 Century 20 or Century 21 on the show floor, right? And that was my first few days with Schlumberger. Schlumberger had a very good time at with Century 2021, which was almost a monopoly here. And the second generation after that was the ITS 9000.
And pressure from Wall Street forced Schlumberger to spin off NP Test, the test and debug machine division.
I actually was not anymore in Schlumberger at that time, right? I had created Sabre, that service division,
Sabre,
right?
That's right.
And then I had at the end of that, I had joined one of my customers called High Connection Density. So I was actually in high connection density at that time, and that's when actually Ashok Belani came back to see me and asked me to rejoin Schlumberger because the chairman had decided to exit the non-oil and gas business, and that as a result of having worked on all of the division, like the diagnostic equipment, and I knew about front end and my background in microelectronics and so on. So, and they asked me to actually work with him and start leading the effort and the divestiture effort outside of Schlumberger. But what was the reason exactly? I think there was a desire to refocus on the core competency.
Refocus on the core competency of the company. So Fairchild got spun out, division of test kept with Schlumberger, which got spun out to NP Test. And then moving forward now with Sapphire in hand, retargeting of the business for a different revenue base, new engineering team, you got acquired by Creedence.
Yes.
How did that transition happen? How was it a easy marriage, obvious one? Creedence certainly was interested in the product line.
Yeah, I think the the product line were very complementary at the time of the merger. Creedence was very successful in the OSAT business. I think that the Vista platform and had come to its lifetime. Sapphire was extremely successful, and a lot of people were jumping on the bandwagon of Sapphire. So Schlumberger and NPTES was finally doing something a little bit different from addressing the very, very high end of the industry. Here was a platform, and a scalable and flexible platform capable of going from
modular to
modularity, from the low end to the high end. Not only that, but mixing low end and high end pin inside of the same tester together with DFT technology. So there was really a lot of flexibility embedded in that test equipment. And I guess that's what the company and what Creedence saw inside of NPTES.
So this is a long history now. Now, how did you make the big transition from so much of test technology and everything else into Universal Instruments? This must be a big change, and yet you have managed to turn Universal around and make it a premier company.
It was already a premier company, but like all long time company, and they go through ups and downs, and sometimes need to refocus on their core competency and so on. But there is a joke about it, and there is the real
reality
story, right? The joke is, I was really trying to find a business that was more difficult to run than test. Right?
Is that possible?
I found it. When we are in test, we say it's volatile, and we are at the end of the tail of the dog. I managed to find a place that is further down the tail of the dog, that has 12 to 14 competitors in the space, and about the same size than the test industry. So yes, Universal Instruments does automation equipment for the assembly of electronic in general. So we span from surface mount machinery to be able to do PCB assembly using SMT technology, to insertion technology to insert component through hole, through the board for ruggedized application or application that have relatively large power structure and power component. And we do robotics and Cartesian robots that are used to do various things like dispensing, snapping, gluing, screwing, assembling together, that are being used either at the beginning of the back end for odd form assembly, components that are a little bulky like shield, or like complex structure on PCB, like connector or very fancy connectors, down to being able to put things together and assemble them and screw them together, like a cell phone, for example, or like a control unit for an engine for a car. So we have a palette of technology here. We can also apply those technology to the back end of the semiconductor now by picking die instead of picking package component, and placing those die with very high accuracy directly on the substrate, such as to do SiP or multi-chip module, or just placing component in flip chip technology face down at very, very high speed. Those are very mechanical, very, very high speed robots, and it's captivating market, which really serve literally the integrator of the electronic system. So we are seeing the product just before it is being shipped to customers. So it's really the last stage between, before the box that is finally shipped to the end customer. So we see all of the electronic industry. That electronic industry is very fragmented in comparison to the semiconductor. Today I have the pleasure to visit customers in North Africa, South Africa, Indonesia, India, so much larger territory. It's very close to the final application, so it's very interesting in terms of seeing the dynamic of each of the segment of market, like automotive versus consumer, versus mobile versus computer. And a lot of people would like to know what I see and what I see in terms of number and capacity in the industry, because we have a very dynamic view of the market in general. It's fascinating. It's slightly different, but it's capital equipment also. It addresses customers that are downstream, so slightly different customers. It's a place where I've been almost able to apply, I would say, 90% of what I had learned through my career in test. So it was a relatively easy transition from that point of view. Obviously, relating to the customer and the technology is very different.
So it's amazing. People struggle to go through one technology line, if you will, and you have made an amazing transition from very high technology testers serving a small market compared to going and serving, a world's manufacturing base. And this first one was limited to semiconductor companies, kind of concentrated in a few spots to anywhere in the world, like North Africa, Indonesia, and everywhere else. And you made the transition very successfully. So,
the passion is with the technology development, and is to be with customers that are transcending technology every day. That's what motivated me when I was back in France and I saw those electronic components in the window of that, electronic, kit reseller, and made me choose that I wanted to be in electronic. It's what keeps me working, 60, 70, 80 hours a week since I've been in this industry with pleasure and the same passion and enthusiasm. It's when you like technology, it's an incredible opportunity.
Well, that's wonderful. Thank you very much. Amazing career and a very successful one all the way through. Wish you many more years of success, of course. So thank you very much for recording for the Computer History Museum.
It was a pleasure to be here today. Great event and an opportunity to be with incredible people and seeing other technologies that maybe have not been touched through tests directly, what I'm doing today, but that are certainly as passionate and passionating for me. Thank you.
Thank you very much. Thank you.